I'm Jay Dingman, owner and head brewer at Barley Mow Brewing Company in Largo, Florida. In this section, we'll discuss recipe calculations. As emphasized in a preceding section of this module, recipe formulation is a critical part of a successful beer and brewery. In this section, we will continue to elaborate on recipe formulation by drilling down into brewing calculations. While today's brewer has a variety of software platforms that can quickly calculate a recipe, each brewer must have at least a basic understanding of how those numbers are determined and ultimately come together to make a great beer. While there are many calculations to consider when formulating a new recipe, this section will deal specifically with four primary ingredients. They are malt, water, hops, and yeast. To assist with explaining our calculations and how they fit into the recipe, we will be referring to an actual recipe for a 16.5 gallon batch of an American IPA as shown here. You may want to print these slides, the next three slides off, for reference later on in the presentation. Establishing the parameters. When calculating the malt bill, the first step is to determine the target gravity or original gravity. In our sample recipe, you can see that our target gravity is 1.057. Typically, the target gravity is a result of the style, but may be manipulated to the brewer's preferences. Next is identifying the finished volume of beer, which is determined by the brewing system. For our recipe, we are hoping to end up with 15.5 gallons of beer in package, meaning kegs, cans, or bottles. So we work backwards to determine the batch size. We anticipate that we will lose some beer to dry hopping and fermentation, so we want to begin with 16.5 gallons in the fermenter. This is our true batch size. You may notice several other volumes on the recipe. These will be explained later in this section. Next is selecting which fermentables will be used and their approximate ratios in the recipe. In our recipe, we have selected standard two-row barley at 93.8%, which makes up the majority of our fermentables. The percentage is simply the percent of the total grain bill that ingredient makes up. We have also selected caramel 40L at 4.1% and caramel 80L at 2.1%. These grains will also add some fermentables, but are mostly for color and sweetness. These ingredients are typical to the style of IPA. Next, we need to determine the efficiency of our system. This step is a little more complicated because it requires us to have some experience with the equipment we are using. What we are measuring is how completely our system completes the extraction of fermentable sugars from the mash. While some fermentables like table sugar are 100% extract efficient, most grains fall between 60 and 80%. Only by actually brewing on a system can we know for certain how well it performs. We will return to this topic in greater detail later in this section, but for now we have determined that our system has an efficiency of 74.2%. It is important for a brewer to keep a detailed record of their recipes since the system's efficiency can vary from batch to batch. Time, temperature, variations in ingredients, and the size of the grain bill are all factors that can change how efficient each brew can be. Moving on to the grain bill. Before we can get into the detail of the grain bill calculation, we must first have an understanding of gravity units and how they are calculated. Gravity units, or GU, are simply a specific gravity multiplied by 1,000. The purpose of converting specific gravity to GUs is to make calculations easier to process. For example, a specific gravity of 1.057 is simply 57 GU. Now calculating the malt bill becomes quite simple. To determine the total amount of extract needed, we multiply the GU of the target gravity by the batch size to determine how many total GU we need. Using our sample recipe as an example, we multiply our target gravity of 57 by our batch volume, 16.5 gallons, to get 940.5 total GU needed. This is how much extract we need to achieve from our fermentables to hit our target gravity. To calculate the amount of extract from each fermentable, we simply multiply the percentage we established for each ingredient by the total gravity to determine the total gravity per ingredient. So for our two-row, we multiply its percentage in the grain bill as a decimal 0.938, by the total gravity units for our recipe, 940.5, to get the total GU needed from this ingredient, 882.19. Applying the same formula to the remaining ingredients, we can see that we need 38.56 GU from the caramel 40 and 19.75 from the caramel 80. Now we need to convert this data into actual measurements we can use in the recipe. To calculate the number of pounds of each ingredient, we need to know the extract potential for each ingredient. This is determined by the efficiency of our mash, as mentioned before, and the maximum extract that can be achieved per 1 pound of ingredient mashed in 1 gallon of water. Rarely will a brewer conduct their own extract potential experiment, so instead we rely on the information readily available from the maltster or found in a chart like this, found in Ray Daniels' book, Designing Great Beers. These figures represent an ideal, yet unrealistic, mashing environment. So first, we must determine our own extract potential by multiplying the ingredient's extract potential by our system's percent efficiency as a decimal. Remember, we've set our efficiency to 74.2%, so the equation looks like this. Here you can see that the extract potential of 2-row is 35 GU. Considering that our efficiency is 74.2%, we can reasonably expect to extract 25.9 GU per pound of 2-row. Using the same equation for the caramel malts, we can see that they have a slightly lower extract potential and therefore will have a slightly lower gravity per pound than the 2-row. Now we simply divide the total GU per ingredient needed by the gravity per pound to determine the pounds needed. So if we know we need to achieve 882.19 GU from the 2-row, and we know that our gravity per pound for 2-row is 25.9, we can quickly calculate that we need 34 pounds of 2-row for this recipe. Applying the same formula to the remaining ingredients, we determine that we need 1.5 pounds of caramel 40 and 3/4 of a pound of caramel 80. Calculating the grain bill is just that simple with one exception. Looking back on the table for extract potential, you will notice that there are various forms of sugar included under boil kettle fermentables. The weights of these ingredients are calculated the same way, except they are 100% fermentable when added directly to the kettle during the boil. In other words, to determine the extract efficiency of these ingredients, we would multiply them by 1 instead of 0.742. Now that you have an understanding of how GU and extract efficiency work in a recipe, we can step back a minute and discuss how they relate to determining the efficiency of our system. In theory, it's as simple as determining the total potential gravity of your recipe and dividing that by the actual gravity you achieve from brewing. In reality, it's a bit of a chicken before the egg scenario that requires some trial and error. To determine the potential gravity of our recipe, we multiply our ingredients in pounds by their extract potential to determine the total potential gravity for the recipe as shown here. Here you can see if we brewed this beer at 100% efficiency, the total GU would be 1266.5. Upon actually brewing this recipe, we end up with 16.5 gallons of wort with a gravity of 57, which means our total GU is 940.5. Divide that by 1266.5 and we determine that our actual efficiency is 0.742 or 74.2%. Calculating how much water you will need is another step that is a balance between what you can expect and what you learn from experimenting. Although water volumes are actually calculated backwards from the finished batch size, to make it easier to understand, we will use our recipe and start at the beginning. The first volume we look at is our pre-boil volume. In our recipe, that is 19.68 gallons. This represents the total amount of wort we need to collect after mashing and sparging. The amount of water we need to mash with is typically between 1 and 2 quarts of water per pound of grain and is mostly determined by a brewer's personal preference or system limitations. For all of our systems, we use a ratio of 1.28 quarts of water per every pound of grain. We found that this gives us the best mash consistency and efficiency. So for our recipe, the total weight of the grain is 36.25 pounds. So multiplied by 1.28 quarts of water per pound, we determine that we need 46.4 quarts or 11.6 gallons of water to mash. During the mash, the dry grain will absorb some of that water at a rate of 0.123 gallons per pound of grain. So again, we take 36.25 pounds of grain, multiply it by an absorption rate of 0.123 to determine that we will lose 4.46 gallons of water to the grain. The amount of water we need to sparge with is determined simply by subtracting the volume of water, subtracting the volume of the mash water, 11.58, from the pre-boil volume, 19.68, and then adding in the amount of water lost to absorption, 4.46, to determine that we need 12.56 gallons of sparge water. The last thing to consider when calculating the amount of water needed for sparging is loss to the system by way of dead spaces and hoses. For example, we have determined that we will need an additional 0.14 gallons to offset loss to equipment, making the total sparge volume 12.7 gallons. Now that we have collected 19.68 gallons of wort into our kettle, the next volume we are looking to hit is our end boil volume of 17.68 gallons. This loss is to evaporation during the boil. With a vigorous 1-hour boil, most brewers expect to lose 8 to 10% to evaporation. Our system is upwards of 10.5%, so we calculate our loss to evaporation at 2 gallons. The reason we target our end boil volume at 17.68 gallons is because we hope to put 16.5 gallons into the fermenter. The first loss comes from shrinkage. Just as wort expands when it's heated, it shrinks when it cools back down. Shrinkage is calculated by dividing the volume we hope to put into the fermenter, 16.5 gallons, by 0.96 to get 17.18 gallons. In other words, boiling wort with a volume of 17.18 is the same as cooled wort with a volume of 16.5. The additional 0.5 gallons is lost to trub. Trub is the leftover hops, lipids, and proteins that remain in the bottom of the kettle after the boil. Since we don't want to transfer the trub to the fermenter, some wort is lost as we leave trub behind. With 16.5 gallons of wort now in the fermenter, we have successfully achieved our batch volume. Through fermentation, we can expect to lose some beer to spent yeast, much the same way we did to the trub. We will also lose some beer in the packaging process to hoses and runoff, making our final package volume of 15.5 gallons. The other factor that needs to be considered when calculating water volumes is the addition of ingredients into the fermenter that will absorb beer, most notably hops. I am continually amazed at how much beer is lost to absorption in the dry hopping process. Next, we need to calculate the amount of hops we will use for the bittering and to some extent flavoring and aroma. By determining how we want the beer to taste and smell, we will determine not only the weight of the hops we'll add, but also when they will be added. Hops are covered in detail in another section, so for this section we will deal primarily with calculating international bittering units, or IBUs, as they pertain directly to a recipe. Calculating IBUs is a bit trickier than gravity units, mostly due to the number of variables involved that affect IBUs. This slide shows the equation for determining the IBUs of a single hop addition. The explanation of the variables is as follows. Weight is simply the weight of the hop addition in ounces. Percent utilization is determined mostly by the amount of time the hops are in contact with boiling wort and is a measure of how completely the bittering alpha acids are released and retained in the beer. Most brewers use a table, as shown in the next slide, to determine the utilization of a hop addition based on when it is added to the wort or beer. It is used as a decimal in this equation. Alpha acids are also used as a decimal and will be determined by the grower and listed on the data sheet that came with the specific hop. 7,489 is used to convert the equation. IBUs are a measurement of milligrams of isoalpha acids per liter of beer. 7,489 converts the outcome of the equation into those parameters. Volume is the batch size that ends up in the fermenter. Here is an example of a percent utilization table based on when hops are added to the kettle or after fermentation. Corrected gravity is a bit more complicated. Since hops react differently in higher gravity wort, any wort with a specific gravity above 1.050 must be corrected. To calculate corrected gravity, subtract 1.050 from the actual gravity of the wort. Divide the difference by 0.2 and then add 1. To calculate the corrected gravity for our recipe, we subtract 1.050 from 1.057 to get 0.007. Divide 0.007 by 0.2 to get 0.035. Then add 1 to get a corrected gravity of 1.035. For all wort with a specific gravity of 1.05 or less, the corrected gravity is 1. So with all this in place, let's calculate the IBUs for each hop addition in our sample recipe. For the first addition of 4 ounces of Chinook at 11.1% alpha acids, added at 60 minutes, the calculation looks like this. For this addition, the weight is 4. Using our table for percent utilization, we see that a 60-minute addition has a value of 0.30. The alpha acids for Chinook are 0.111 multiplied by 7,489 gives us a value of 997.53. Our volume is 16.5 multiplied by our corrected gravity of 1.035 gives us a denominator of 17.08. Divide that into 997.53 and we determine that the IBUs for our first hop addition to be 58. Now let's take a look at the next 2 additions. Notice how quickly utilization drops as the hops are added later in the boil. This coupled with smaller weights and lower alpha acids cause these additions to have a much less significant impact on IBUs. Still, this beer comes in at a healthy 85 IBUs. Notice that there are 2 other hop additions that do not contribute to the IBUs of this recipe. That is because they are dry hop additions. Because they never come in contact with boiling wort, their utilization percent is 0. Which brings us to an important consideration. It should be noted that there are 2 types of hop additions done during and after the boil. The first is for bittering and includes all additions that come in contact with the boiling wort for 30 minutes or more. The other is for flavor and aroma and are only in contact with boiling wort for 0 to 30 minutes and include hops added during knockout and dry hops. While it is important to calculate the IBUs that flavoring and aroma hops may add to the overall bitterness, the first consideration for these additions should be how they will affect the flavor and aroma. Since those flavors and aromas are a result of essential oils found within the cones, there really isn't a simple formula for calculating how they will impact the flavor and aroma. In fact, for as much as we know about the compounds that do contribute to these characteristics, much of the decision making of how much and when to add these hops falls on the preference of the brewer. Experimentation is key to calculating late and dry hop additions. While this basic equation is fairly accurate at calculating IBUs, utilization will vary from brewery to brewery. It may take a brewer several brews before they dial in their utilization, especially for a brewer without advanced laboratory equipment to measure exact IBUs. As we mentioned in another section, yeast is considered by most brewers to be the one ingredient in beer that has the greatest impact on the final flavor of the beer. For this section, though, we will focus specifically on determining how much yeast to pitch. To calculate the proper pitch rate, all a brewer needs to know is the original gravity and volume of the wort. The basic equation is 1 million cells per degree Plato per milliliter of wort. If you are unfamiliar with degrees Plato, it is simply another way of measuring the specific gravity. Using our sample recipe, calculating the pitch rate would look something like this. First, our specific gravity of 1.057 converts to 14 degrees Plato. Second, 16.5 gallons of wort is equal to 62,459 milliliters. So multiply 1 million cells by 14 degrees Plato and then by 62,459 milliliters of wort to determine that we need to pitch 874 billion yeast cells. It should be noted that yeast reproduce so quickly that this number represents the best practice, but not necessarily an exact amount needed. While underpitching and overpitching can both produce off flavors or catastrophic results, recognize that this number is not an exact measurement of how much yeast needs to be pitched. Calculating how many yeast cells needed to pitch for a healthy fermentation is just the beginning of actually pitching. Yeast typically comes in 4 forms: dry, liquid, slant, and slurry. Slurry is yeast harvested from a previous fermentation. Each form comes with different levels of viability and volumes that will come into play as a brewer decides how much to use. For the purpose of our example, we will use 11.5 gram packets of dry yeast. Dry yeast typically contains about 20 billion cells per gram, or 230 billion cells per package. So long as the yeast has been properly stored and hasn't expired, we can expect that 4 11.5 gram packages should be sufficient for a successful and healthy fermentation. This concludes the section on basic recipe calculations. As mentioned earlier, there are hundreds of software platforms available to brewers these days, but a solid understanding of these calculations will help a brewer when setting the parameters of their software or when sourcing substitute ingredients. They will also add to a brewer's overall understanding of their craft.